The final talk of the session is on detection and containment of emerging diseases using AI techniques. And the speaker is Professor Alberto Sangiovanni Vincentelli from the University of California at Berkeley.
So I'm here to talk about a research project about the detection, early detection of COVID or other pandemics, because it's everybody's feeling that this is not the last pandemic that we're going to see. So what can we learn from what we have seen to fight the new pandemic when it comes about? So this project was consisting of 4 different thrusts, because it's a complicated matter. So we had a first thrust that was related to the rapid identification of an emerging disease. So something is happening. Guys, pay attention. So that was the first step. The second one is, once you find out that there is something new, how can you adapt what you have done before to this new disease? Because there are things that we know how to do that could be shifted to cope with the new situation. Then, how do we develop robust methods around the world? And the fourth step was, can we do collaborative AI for healthcare, where humans are involved in the loop? We learned that that is an important point from other speakers, and I was always convinced that you need human in the loop of anything that has to do with statistical techniques like the ones that AI bring to bear. Now, this project was very ambitious, and so we had a number of people involved. Now, one word about funding dimensions and ambitions, right, about doing large research programs. Now, this research program would not have been possible if we didn't have other sources, right? So the point is, if we want really to have an impact, like the DARPA grant in the old times, then you need to summon many other resources to be able to do something reasonable. Because with the amount of funding and the period of funding that you have to deal with, is not much that you can do. You can do something, but not solve the world's problem. Now, the other important thing that I wanted to stress is that in our team, we have a doctor. We have a medical doctor, a surgeon from UCSF. And that gave us the domain knowledge that is so important when you try to cope with medical situations. So you got the computer scientist, the electrical engineering expert, plus medical experts that are going to verify that what you do makes any sense. Now, another important lesson that we learn is that if you do include people from other backgrounds, you better find someone who understands you. And the point is, Jeff Tyson is a surgeon, as we said. It works at UCSF, but he has training in artificial intelligence techniques because he's employing artificial intelligence techniques to cardiovascular diseases. So we could interact. This is very important. Anytime you do interdisciplinary research, you have to speak the same language. Otherwise, you don't go very far. They don't understand you, you don't understand them, disaster. Okay, say this. Given the magnitude of the project, we decided to focus on one point that we found interesting and that we got some interesting results as well. Now, this particular research has been done in collaboration with a number of people, and Hari Prasanna Das is here with us. And if you have any specific question about the techniques used here, Hari is here to talk to you. He's also as a poster in the afternoon. So what is the goal of synthetic data augmentation? So we said COVID was a surprise. So we had a few cases that started developing, and then we wanted to see whether, with the scarce data that you have, you could use AI classification techniques to detect this particular disease. Now, since the data are scarce, because it's the beginning, you don't even know what you're facing often, then the problem is, how can we train a neural network, right? Or any statistical model for that matters. We need cases, otherwise we have a problem. So in general, we had unbalanced cases. So we had few COVID, lots of other diseases like pneumonia or other things. So how do you balance the information in such a way that your trained models give you some reasonable insight, right? This could be used also for all the cases where we have bias, right? So we say that, for example, for hiring people, we can use AI models, but then if they are biased because you are based on the past, and in the past, for example, for certain jobs, certain kind of people are not there, but they could be there. And if you base the hiring decision on what you have seen before, your host. So how can you generate synthetic data that mimic the possibility of other people being in that topic? So the flow of our methods go from the data sets, when we do synthetic data generation, and then we have the expert validation of the results. So we had our medical doctor that could say yes, no, BS, or good results. Okay. So how do you generate a synthetic case, right? So you got something that you know is COVID, but you don't have enough of that data. So one way in which you could do it is to try to keep the characteristic of the disease fixed, right? So if you have a characteristic feature extraction, you keep it there, and then you change everything else, right? So in that way, you're guaranteed that this one looks like COVID, even though it's not, because you change, it's not something that you have in the database, because you change something that is not really ruining the information about COVID. So that's the idea that we follow to build our techniques. So we have COVID and non-COVID data. So now we take the train data with a encoder that builds a conditional feature representation, and then the last two layers are the one that are classifying if what you have seen in the features is COVID or non-COVID. It's classical, nothing new here. Now, in parallel to this, we also take a conditional generative flow that does a forward pass, but keeps the information about the feature representation as an input. So what that does is that it generates an output, which is a local representation of the information. Notice that the conditional generative flow generates a nu which has the same dimension of x, while z is a much reduced vector because it's the encoding process. It's the important information that you want to keep. So in some sense, nu represent everything that you have thrown away, if you like, that you have actually identified here. And so every information that was in X and is not in Z is here. Now, since we said before that we really want to keep the characteristic of COVID, but we want to generate synthetic data by sampling what is non-characteristic of COVID. And so how we do that? Now remember that for the flow methods are invertible. So if I pick up sample V space, which is different than what I had before, and then if I still use Z as an input here, I can invert this flow and generate another input here. So there are a number of people that have dealt with this kind of problem. In particular, the closest paper here is the one that Ma et al. That had a similar architecture, except that they did unsupervised learning, and they didn't extract this conditional feature that I'm talking about. And in fact, the generation of the additional cases go through the classification. Then you siphon off the Z vector here, and then you sample a local representation. You put in the inverse flow, and you get the new image that you are going to add to your training set. Okay, so that's the in a nutshell what we do. So mind you, all what you see here, can I prove anything? No, I cannot. There are some things in the method itself that you can say, well, this is reasonable or not reasonable. But in general, everything that has to do, unfortunately or fortunately, with this kind of techniques cannot be proven, right? So this is heuristics, and being heuristics, the only way in which you have a way of saying I'm good or I'm not good is running tons of test cases, all right? So we use a test case as well. Now, is that useful? It is, especially when you don't know the models. And I don't even have the faintest idea how you can generate model for the shape of the COVID lungs, right? So this is okay for that kind of application. When you have physics, please, please, please use that information. Don't just throw everything, boom, to the neural network with millions of parameters and the like. Now, in the part of the encoder, we have a particular architecture. It's called COVIDNet, right? Now, with several layers, the convolution and so on and so forth, the different parameters of that. Can we prove that that is the best? Absolutely not. And so the general procedures that you follow is that you get something that is reasonable, you check it out. If it works, you say, hallelujah. Now, then the scientific method would be, let's try something else. But there are too many variables to play with. And this is a problem, a generic problem with the kind of techniques that we use. So what is a test case? So we got healthy, 45,000 images, common pneumonia, 36,000, and then 21,000 of COVID, okay? Now, notice that we combine these two, right? Because we want only COVID, non-COVID. So, well, with this kind of techniques that I showed you before, a way to see if it works or not is to do the conditional synthetic data generation and then classify only on the bogus test set and train set and compare it with the real data, right, and see what happens. Now, if the two are close, then it means that you got something, right? And in fact, you know, guess what? Our method, hallelujah, is the best there is and all of that, okay? So I'm going to believe anything different, but that's what we got. All right. So there are other methods that have been compared. It's surprising that what I think is a very good architecture and the like has this kind of results, which are very poor. But why are very poor? Because it's an unsupervised learning there. Okay, and we are supervised. So, well, there is a method in which you can evaluate how good you are with respect to the real case, and that is called the Frechet inception distance. It's a qualitative measure and gives the difference between the distribution of some set and another set. And so the difference here is small. It means that our distribution is close to what is real on the generative data. Okay, so that's the original sample. These are the synthetic samples. And you can see, well, you cannot see how you generated this, but that's the way we do it. You pick a reference point, and then you do the sampling of a distribution, you invert the flow, and you get this data, okay? So they look kind of similar, but not that similar. Now, the other problem in this domain is the fact that you may have data that are not fully labeled, so, or the label are iffy. Now, what do you do? I mean, the more labeled data you got, the better it is, of course. If you have data that tell you this is COVID, non-COVID, but you don't know what are the labels, the information about this particular image, then there is a problem. How do you label this data? Okay, so there are techniques to do that, and the way in which we do this step is to take what you have and with the labels, then you train the network, so you get the conditional feature representation, then with that conditional feature representation, you do a nearest neighbor-based labeling of the unlabeled data. And with that, you transform the unlabeled data to labeled data. How you do that? You use a greedy algorithm that takes the representation of this in this domain and then finds the closest label image to that you are trying to classify. And then you assign the labels based on this information. Okay, so then again, you do the forward flow inference, you get local representation, then you generate the additional data set using the same algorithm as we did before. Now, this combination of techniques to label the data and the synthetic data generation has these results that you see here. We took very few samples that were labeled, a little bit more, a little bit more, more, okay? And so you see, of course, that the more labels you give, the better results you get. But the important information is that only with 5% of training samples that are labeled, you get already to the close to the ones that you would get by 100%, okay? Which is an important information to have. Now, notice that even 1% or half of a percent in this case is substantial. So anything, so don't underestimate the value of the 95% of the things that we have not considered when we do 5% of the training data. So this one is doing a different synthetic set generated, this case with random seed, the results are similar. Then you give this generated set plus the one that were labeled, you combine them together and you say, how much better am I if I didn't have the synthetic data generation? And you see that you get, you know, close to 1% here, again, 1.5% here, again, of the order of 1 to 2% better results. As we said before, 1% is still very significant in the case of AI, alpha application. So in synthesis, we adapted existing healthcare AI tools to the case of scarce data by generating artificial data, okay, or synthetic data. Thank you. Shankar. You can scream enough. Okay.
So I think you really, but all of you in this session, this sort of this notion that there is the data is you needed to generate synthetic data in order to be able to augment the data, and you talked about hiring and how it is that if you if you believe only in past data which has biases in it, the future will look like the past, and we don't want the future to look like the past, and that's why you're doing it. But now, right, then, there you are. Also talked about, so you get to modify the data, that's one. The second one is about really modifying the cost functions and to choose the cost functions.
Yeah.
And that is also good. And so, to me, so let me just put them all out a little bit like a kitchen sink, but I hope you have it all organized. But then, to me, I think also seems that the other thing that you said was the explicability of the conclusions of the deep neural network is quite often, explicability consists of saying that there are low-dimensional features embedded in this high-dimensional data, and in retrospect, you say this, and so you validate this. So tell me a little bit about how you think all this, how do you organize all of this? And you said, the other thing that you said, which is your most recent project, if there's physics, use the physics modeling. So if you could just sort of sort out all of this.
Well, I mean, for example, if you, the standard techniques in this kind of encoder is just you fix a dimension, like say 32 is the dimension of Z, right? And then you use a neural network to put numbers in this Z vector, right? So the only information you give is the dimension of the vector. Now, if you know some physics or some important information about dimensions of a problem. So, for example, you can say that white cars against a sun are less visible than black cars, right? So that you know. So the color is important, right? But if you have radars, does it matter? No, it doesn't, right? And so this is physics, right? So you could put that information in the sense that if you are trying to not to crash into a car and you have radars, color doesn't matter. So it's not going to be in the z vector, if you like. If I am with cameras, then in the z vector, I'm going to add color and time of the day, right? Because it's the sun combination with the color, right? So if I have this kind of information, I could build a z vector that contains a physical information in some sense, and it will give me a better compression because it is the latent information that I'm really looking for. So you hope that the neural network is going to extract that information, but sometimes it doesn't. So if you bias by saying, look, one element of a z vector is this one, then I think you can improve and put physics into the neural network, if you like. But then we talk about neural network, but essentially is a model, is a black box model. And we say neural network could be support vector machines, could be polynomials, could be sinusoids, you know, whatever, right? A combination of exponentials. And neural networks happen to have some characteristics that for most cases we don't know. It just happens to work, right? But I would really like to have some demonstration that neural networks are any better than any other method, right? So, and by the way, talking about physics, right? If you look at the best performance of neural network in general are in the visual image recognition. And guess what? Neural networks look like our visual system, more or less, right? In the way in which we process it. So there is still physics in it.
So I'm curious. You're saying we don't know physics, yet your synthetic data generation model made a very specific assumption. It said, this COVID I'm going to keep constant
Yeah.
and vary everything else. And the assumption is that this is independent of everything else. And that's your physics. You're
in some
basically
sense,
imposing
right.
your physics by generating that data.
I would like to be able to say that that z vector is the real thing, right?
But that's what you did, right? Because
in some sense.
right, implicitly.
Implicitly.
You imposed a model. Well, you did explicitly. The model picked it up implicitly.
Exactly.
And the question is, like, how correct that assumption has to be for, if that was totally wrong.
All the bets are off.
That's right. And so the magic isn't coming from synthetic data. The magic is coming from your assumption.
No, absolutely. But the synthetic data is the way in which you keep what you know and you enlarge it in such a way.
Because we train on labeled data.
Right, exactly.
So that's kind of what my question really is. What if we just got rid of the gymnastics of like, just get rid of this synthetic data thing and say, I'm going to impose this constraint on top that says, this can be held constant and this is independent of everything else.
Right.
If you impose that explicitly, you sort of, you model that more directly. And I wonder, like, is that a more feasible but harder way to
well, I mean, this is definitely what I would do if I knew something about the physics of the model. No question about it, right? Since I don't know, as I said, I don't know how the lung of a person with COVID looks like from physical point of view, then I do have a problem trying to figure out what is that kernel of physical information. Now, as you said, when you say, okay, this is my compression value, right, I'm already making an assumption that that vector is sufficient to represent the truth, right, whatever that is, right? Now, can I reinterpret back into this vector and that is explainable AI? If I could interpret back Z, what the heck is Z in physical terms, then I would have explainable AI. Do I have it? No, I don't think that we can.
I'm going to add on to that since the conversation is going well. So when you evaluate your system, I'm assuming you do it by the whole scan, all the images, the whole by case. But when you're doing the generation of the synthetic data, it appears you're doing it slice by slice. So if you were to do it for one slice and then do it for the slice next to it, compare how they come out, because if there's a lot of similarity from one slice to the next. And I wonder if you were able to look at that.
Well, I don't know, Harry, did we do some experiments like that? But in any case, the point is that, again, since we keep the z vector constant, it's likely that the two images will look not too different.
Good check.
Right, yeah, no, absolutely.
So it sounds to me that your need for all these images, synthetic images, is because you have to estimate all these parameters in the neural net. Now, and yet you are saying that everything is anchored on your knowledge because everything else is subservient to that one constant anchor point. So suppose I said, don't use neural nets. Just look for that one thing.
Okay, right.
Then you don't need all this exercise.
No, of course not. But the point is, again, the neural network brouhaha, right? The issue of using models that learn, right? So what is all about is the fact that I don't know really the physics of it. I keep on repeating, harping the same theme, right? And so it is a statistical model.
But your assumption, it seems to me, is that there is nothing to learn in the stuff that you're adding to the anchor point. So the anchor feature is the critical thing.
No, well, I mean, there is, no, absolutely. The kernel, the thing that you keep constant, of course, is the critical feature. Now, the reason why I'm doing this is because in the global diagnostic thing, I'm going to use a neural network, right? A classifier neural network. Now, if I have too few images, if you like, then I'm going to be biased, right? So this is a method of eliminating some of the bias in the data, right? So you balance the set of data by adding something that it resembles to what it was supposed to be. But you are right. I mean, the whole theme is that if we cannot do otherwise, it's fine to use neural network, otherwise don't use it, right? Because you throw away centuries of intelligence just by going with a generic general model. But indeed, I mean, it's one of the many, right, that you can use.
So
That's my point.
maybe we can continue this over lunch. Let's take this opportunity to thank all the speakers for the talks.